Hello and welcome to All Space Considered. My name is Dr. David Reitzel, and with me tonight is Chris Butler. Um, and also we have a whole bunch of our crew with us tonight to talk about the American Astronomical Society meeting. It's going to be kind of excited. So we've got Daniel Perea with us. We've got Sarah Vincent. We've got Haley Bricker. We've got Bill Gruneberg. Katie Flynn, of course, is going to do her regular segment. And we have a very special guest as well that I'm excited about tonight. Tonight's program is brought to you by the Department of Recreation and Parks, the City of Los Angeles, and of course, Griffith Observatory that's owned and operated by the City of LA. We are coming to you not quite live from Griffith Observatory, but tonight's show is definitely live. It is not a Friday. I know our up there, it says the first Friday of every month, but we're doing tonight's show on a Thursday, just because we thought we'd try it out. We'd see how it went, and we'd see how many of you tuned in. And it looks like we lost a few people along the way, but this is the second Thursday of the month. It's not even the first Thursday, so we've completely fouled it all up. But the first of the year was just a little too close to the first Friday, and then we thought, well, let's try out Thursdays. As long as we're not doing it on the first Friday, let's see how that goes as an experiment. So tonight we are on the second Thursday of the month. But tonight, like I said, we have yet another special guest. There's a whole crew with me tonight, but we also are very excited to have Anthony Cook back with us. In case you're not aware, Anthony Cook was our astronomical observer. I was going to say telescope observer, but astronomical observer at Griffith Observatory, and was a major member and huge contributor and panelist on All Space Considered for 14 years or something, 13 years, ever since the beginning of it. Tonight we're just going to catch up with Tony, and he's going to tell us a little bit of some things we can observe in the sky. In particular, there's a pretty great comet that you can get your eyes on if you have the right way to view it. We're of course going to do pretty pictures and some solar system weather with Katie. We do have a sky report, and you notice, where's Patrick? All these folks are with us tonight, but where's Patrick? Well, Patrick's on overnights, making sure that the Samuel Ocean Planetarium is in top shape and is in absolutely tip-top shape. So he's off doing that. And then we're going to do, but we still have a sky report from him. He put it together ahead of time, so we'll see what he has to say for us. Then we're going to do a large segment on the American Astronomical Society, number 241. That meeting is going on, well, right now. It finished today, but the astronomers are still in Seattle, and that's where the meeting was. And we have reports from that meeting for you. And then poor Chris Butler has to wait the whole show before talking about years ago today. Now, I will find out how many years ago today he's going to talk about, but it's a brand new segment that we're bringing to All Space periodically years ago today. So we hope you enjoy the show. As always, we want to make sure we thank Griffith Observatory Foundation, who's our nonprofit partner with Griffith Observatory on so much of what we do. And I do want to thank all of our donors and all of our members and everybody that makes what we do possible. So thank you. Tony, let's begin our conversation tonight with Tony and Anthony Cook. It sounds so formal.
Tony
Cook. Tony, you've been interested in telescopes and making observations. Well, it was pretty much your whole career, but when did you first get excited about telescopes?
Well, I got excited about the sky actually when I was 4 years old, because my parents took a trip to Griffith Observatory. I went with my grandmother and parents, and my parents went into the planetarium show, but Grandma had to stay out with me because I was 4. And it really got me wondering, what is it about stars you can know about when you're 5 that you can't know about when you're 4? So sure enough, when I turned 5, I got to go to the planetarium, and they were doing a show showing the winter sky, and they showed the Pleiades, which appropriately is in the picture here. And when I went outside, I recognized them right away. I said, "Oh, they showed that in the show." So ever since then, I got interested. I got a telescope shortly afterwards, one that, I would probably say is inoperable now. It was a really bad one, but nevertheless, I could see the Pleiades through it, for instance, and I got interested in constellations and how to find things, and by third grade, I was giving talks about what I was seeing through my telescope and boring people already. So,
Yeah, and then you were a museum guide at Griffith Observatory, and then a
that's right.
telescope demonstrator, and then eventually
Astronomical observer.
astronomical observer.
Yeah,
So
yeah,
you do know a lot about telescopes and observing things. And right now, there is a comet that's observable. Is that the one in the picture we're seeing here?
that's right. It has a romantic, beautiful name. You know, these things are named for their awesomeness. It's 2022 E3 ZTF.
Now, 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 why don't you tell us a little bit about it? I know you prepared some slides for it, and I'll just let you take it away for a while. And unless we have any questions, we won't interrupt you right away. But
Sure.
let's hear about
Well,
this comet.
okay. Well, I mean, basically, you may have seen, I mean, it's already hitting the news, a green comet to light up the sky, things like that. And that seems to be the main headline. It's kind of like supermoon. It's something annoying that the news always says whenever there's a bright comet in the sky. I don't think you'll see it looks green necessarily. Now, it's green in pictures, but uh, basically, this is a comet that was discovered in 2022. In fact, this is where the name comes from. It's called C-2022. That just means a comet discovered in 2022. E3 tells you what part of the year it was found. So E is the fourth letter of the alphabet, and it's the fourth 2 week, fourth half of a month of the year. So the first half of January is A, second half is B, first half of February is C, then last half is D. So the first half of March is E. So that tells you it was found in the first half of March. And then the 3 simply means it was the third comet discovered in that part of the year. And this fairly recent naming convention is made because now there's automated surveys that are finding far more comets than were found before, and older conventions just couldn't keep up with all the numbers that were being found. So this is a way that should hold us for a while. The ZTF, in fact, whenever you want to go to the slides, I actually have a picture of it. The ZTF has a relationship to Griffith Observatory, actually. It means the Zwicky Transit Facility. Fritz Zwicky, of course, was an astrophysicist who's famous for coming up with the idea of the supernova, along with a lot of other ideas. Because he was interested in supernovae, he was interested in getting high-quality, wide-angle pictures of the sky, so he could start getting statistics on supernovae and galaxy clusters. So when Palomar Observatory was made, they added to its list of things to do a large Schmidt camera. And a Schmidt camera is just a camera that photographs in as high quality as possible a huge area of the sky. So for a long time, it was known as the Palomar 48-inch Schmidt, and it opened about the same time the observatory did. It made the first survey of the entire northern hemisphere of the sky, and then similar telescopes in the southern hemisphere completed that survey. In the 1990s, I guess, it was turned into the Samuel Ocean Telescope because the film equipment had been taken out of it, and instead electronic detectors put in. So in the big picture, of course, in the observatory is made from pictures made with this instrument. Now another set of electronic cameras have gone into it, which are kind of pushing the new technology of observational astronomy. And these are high-speed surveys of the entire sky. So Caltech has been doing a lot of work. A lot of it's actually classified as to how this telescope can really look at the entire sky in a couple nights and record every supernova, comet, asteroid, everything in it. And it's all automated. So basically, I've been told that the astronomer has said, is given a program that tells them on their phone, here's the interesting things you might want to look at. Okay. So back in March, one of the interesting things that astronomers were told to have a look at was a comet. You see the names of Bryce Bolin and Frank Matchey, who apparently are Caltech astronomers who were the ones notified, but nevertheless, it was named after the ZTF telescope. And now, a lot of comets are found. This one wasn't, well, it was bright for its distance. I can't remember. It was found out, past Jupiter's orbit, but it was already relatively bright for something that far out. And what's been interesting in the last few weeks, it's developed a bright tail, and why don't we go to the? Oh, I'm sorry. Actually, I know. I'm supposed to go over to guacamole, right?
Exactly. Get yourself a snack and some guacamole.
All right. So I'm there now, and this is my first time. So if I do something wrong, please say so. All right. So what we're looking at is a picture of the comet's orbit. One of the first things found about this is that the orbit of this comet probably takes at least 50,000 years to complete. At least it did until this passage. It may be that this passage will just accelerate it just enough to throw it out of the solar system entirely. But in any case, it hasn't been near the Earth in thousands of, or tens of thousands of years. So what we're looking at here, the little oval, the bright oval near the center, is the orbit of Neptune. And this thing goes out 28,000 astronomical units, which is why it takes so long to complete. Here's a picture of it taken back in October. These pictures are all by Michael Yeager. And Michael Yeager is a photographer who really just specializes in comets. There's a lot of people who take beautiful pictures, but Michael Yeager is the most dedicated I've seen just to comets. So these are images you'll be seeing that he got up until last night, actually. So this is what it looked like back in October when it was still quite distant from the sun, and already you can see, yes, it has a bright green coma, and probably larger than the sun, actually, at that point. And then already a tail that's quite long. All right, so we'll go to how it's developed. Here we see it in January, the beginning of this month. It has a bright coma still green. In fact, it's kind of interesting. It's half white, half green. So apparently there's a lot of dust coming out on the sunward side. The blue tail is the ion tail of the comet. And ion tails kind of tell you which way the sun isn't. It's the charged particles from the molecules in the head of the comet that are electrically charged and streaming back with the solar wind. So they generally point away from the sun. But the dust tail is dusty particles that are ejected from the head of the comet and are left behind in the orbit. So they actually spread out and form a big sheet behind the comet's motion. And it's interesting that it's already so developed. Generally, comets that are dusty are the ones that are the most interesting to see with your eye. Now we'll go ahead to the 4th of January. And basically, it's just getting brighter. Now, around shortly after this, the moon began to interfere. But just in the last couple of nights, the moon is dimmed enough that people have been able to get it. This is actually last night. And we see the dust tail has grown. Also, the interesting thing is today, the comet is at its closest point to the sun. It's at its perihelion. So from here on out, it goes out away from the sun and not to return certainly before another 50,000 years and maybe never. It just depends on if, like a planet that it passes through accelerates it ever slightly so much, it would be enough to eject it from the solar system. And right now that's uncertain. Now, visual observers have been watching how this brightens, I should say both electronic images and visual observations allow this light curve to be made. And we see that it's brightening. The smaller numbers mean that it's brighter on the left-hand side of this graph. and you see the date running along the bottom. So the comet is brightening. Remember that the faintest stars you see with your eye are roughly 6th magnitude. The brightest stars are either 0. Well, the very brightest star, Sirius, is minus 1.5. We won't talk about the sun. We're talking about nighttime stars here. But basically, the smaller the number, the brighter. Each magnitude is about 2.5 times brighter than the next one. And already tonight, it's about magnitude 6.5. So it's possible that somebody in a really, really dark sky could spot this with the unaided eye. It certainly is visible in binoculars, and it should get brighter than magnitude 5 in about 2 or 3 weeks. So now that's not a spectacular view, but in binoculars it might be very, very nice, and it certainly will make for great photographs. Just a few things coming up. This is what the comet's orbit looks like up close. So we're just seeing that part of a parabolic curve you see running through the solar system is the path of the comet, just the tiny part of it that's closest to the sun. And here we see where it is tonight. So it's kind of above the Earth, if you can imagine, and it's closest to the sun. So it's a little over an astronomical unit away from both of them. Now, comets can brighten even after their closest point to the sun, because the heat that the nucleus is receiving from the sun takes time to percolate into the nucleus. So just as the hottest part of the day is not right at noon, it's usually a couple hours later because of that similar kind of heating delay in the atmosphere. Comets can actually become a little bit more active after they're closest to the sun, and the tail and all will continue to get longer and longer. An interesting thing may come up on around the 26th of January. This is when we'll be seeing the comet in the plane of its orbit. So instead of looking like a bright, broad, open fan, we'll be seeing all of the comet edge on, and that will make the tail look a lot more solid. That might be the best time for binocular viewing. And finally, late in February, or early in February, the comet goes through the plane of the Earth's orbit. And it will be closest to the Earth actually around the 26th, the date I mentioned before. I just put through these in partly because it's Halley's Comet, and I'll make one other mention of it here. But how a comet appears largely depends on where the Earth is with respect to the comet. And a lot of people remember the 1986, well, a lot of us older folk remember the 1986 appearance of Comet Halley being sort of disappointing compared to maybe what we were expecting. But actually the comet behaved the way it was supposed to. The reason it looked maybe a little disappointing is that when it was closest to the Earth in April 1986, it was also outside of the Earth's orbit, and it was highly tilted to our point of view. So the tail was very spread out. We were viewing it kind of head on, and this made the tail look very, very thin. One way of thinking of this is if you look at a table with a glass cover and it has a little bit of dust on it, you can't see the dust very well if you're looking at it from a high angle. But if you go down to the level of the table and look along the top of the table, the dust looks very thick and it's easy to see. Oh no, I didn't clean that. Well, a comet tail is a little bit like that. The more edge on you view it, the more substantial it looks. And here's the comet at the same distance from the sun, but the way it looked in 1910. And it's not the comet that was different. It was just the viewing angle was close to the comet's orbit. So it looked a lot thicker at that point. So anyway, we can look for it in the sky. It's currently just before dawn. It's moving out of the constellation Corona Borealis right now. So it's in the northeast part of the sky and fairly high up at dawn, and it's moving kind of it'll be moving between the Big Dipper and the Little Dipper, the North Star, in the next few weeks. So it should be easy to spot in binoculars. It's near bright stars that if you're interested in constellations, you probably already know. So it shouldn't be hard to find. Even if it's not visually spectacular, it should be great with photographs. So if you have a telephoto lens, it's in a part of the sky that doesn't trail very fast, so you can try exposures just on a fixed tripod up to like a minute or so with high ISO and your camera lens wide open, assuming you go out to a dark place, say like, Joshua Tree or something like that, and assuming it's not raining, you could probably pretty easily get some nice pictures.
Yeah,
So,
and I want to encourage folks to send those pictures to us here at All Space Considered. Tweet at us, email us, send it to us on Facebook, wherever. We'd love to see your pictures of this comet. So, Tony, I wanted to ask you, why is it green? Why is the comet green colored?
well, it's due to the molecules in the coma that were ice in the coma until the sun's heated it. They've broken free, and let's see. I guess these have carbon compounds and water compounds, but they produce a green emission line as they become ionized. As ultraviolet light from the sun strips electrons from the atoms of the gas, it can produce lines that are predominantly green. There's also a lot of ultraviolet and stuff your eye doesn't see.
Okay. Yeah. I know that diatomic carbon can have greens in it. And anyway, interesting. Super, super interesting. Have you seen the comet yet, by
I
the way?
haven't. I tried actually on New Year's. I set up my telescope and started taking pictures, but right then is when the high clouds began moving in, and I had so much reflected light just from the clouds, even though the air was very clear, I couldn't get anything. And within minutes, literally, the sky clouded over, and I haven't had a clear view since. Even last night looked very beautiful out, but there was a lot of cirrus actually. The
Okay.
moonlight wasn't a good combination.
Well, have you gotten any interesting photos to share with us since you left us? Anything you can
Well,
show off?
I guess I sent in some just to show what I've been up to since I haven't been at Griffith. So I've been experimenting in, I've mentioned this before with lunar and planetary photography and deep sky objects and stuff. So these are just some images I got with a 10-inch telescope in my backyard. And these were
That's stunning.
Well, thank you. These are made using video and averaging thousands of frames with, software called Auto Stackered. And then what you end up with a uniformly fuzzy image, but it has all of these average of thousands and thousands of frames. So the software sharpens it based on the assumption that it's all evenly fuzzy, and you get an image that's just about as sharp as if your telescope was in space. It's really at the diffraction limit of the telescope. So, I know Chris Butler's out there. He probably has the names of these craters on the top of his head more than I do.
Maybe
I
a
don't mean to
couple.
put you on the spot. I know the
I
rock
think it,
gazelle and
I think Alphonsus is hiding in the mix, and
yeah.
Arzactal and a few of the others. But Alphonsus is the one the center with the small
Theophilus, I
central
think is the
peak.
other one. Yeah.
That's right.
Yeah, and our Rakazel is actually interesting because the first director of Griffith Observatory, Dinsmore Alter, continued observing the moon at Mount Wilson Observatory after he retired from the observatory in 1958. And he, along with the Russian scientists, thought they saw a glow coming from that crater. And the Russian astronomer actually photographed a spectrum showing carbon absorption, or showing some kind of absorption lines. I don't think they were identified. And Alter thought he saw evidence of it in his pictures. Now, honestly, I don't see them. I've seen his negatives and stuff, and
Yeah.
I don't see what he was talking about. But the thing is, this increased interest in this crater quite a bit because a few years later, Jet Propulsion Laboratory was attempting to crash camera-equipped spacecraft into the moon. And once they started working on the last 3 of 9 tries, the last probe, Ranger 9, was targeted towards the areas that Dinsmore Alter had been studying to see if there was any evidence of eruptions. There are interesting discolorations around craters, but
Yeah.
We don't think there's active volcanism, but there could be some kind of outgassing, I suppose.
So now you also managed to get a picture of one of my favorite galaxies. I know.
That's right.
To us.
And here it is. Andromeda, or the M31 galaxy, our nearest big neighbor in space. I mean, after the Magellanic Clouds, of course. And then, of course, it has two satellite galaxies too, which let's see if I can do this right. There's one here. Oh, I don't know if you're seeing that or not. Are you seeing?
No, you click on it and go down to laser pointer.
Okay, click on it. Okay.
Yeah, there you go.
There you go. Okay, so I'm sorry. Here's one of them. This is, oh boy, is that M110 or M32? I'm not sure.
I think that's M32.
Okay, and then this is M110 down here, and it's the other satellite galaxy. And then of course,
I know it's the NGC 205. I think.
Yeah. But the M numbers are just named for Charles Messier, who was a comet hunter in the 1700s, who kept finding fuzzy things that he got his hopes up that he had discovered a comet, because that was his only interest in life. But he was disappointed to find they were permanent parts of the nighttime sky and not comets. So to avoid constant disappointment, he made a catalog of what objects that he spotted and what other people spotted. The first list of 110 objects that are, actually still sort of cherished as some of the top things to look for as you start your career looking through the sky with a telescope if you're an amateur astronomer. Okay, so one of the first catalogs of deep objects. Well, here's the Pleiades, and this is one of the most recognizable things in the sky, at least I discovered as a 5-year-old. The Pleiades, of course, have been known ever since people had eyes, so nobody can really be said to have discovered it. But because of its hazy appearance in the telescope, Messier did include it in his catalog as number 45. And it's a bunch of fairly recently formed stars, hot blue young stars, that are passing by a cloud of dust and scattering light as they pass by. So 440 light years away. And then another recent image I got is this one. Now, I don't think these are award-winning pictures. In fact, this one has a serious problem because the camera was a little tilted, so the stars at the upper part are a little bit out of focus. But what I was trying to achieve with this is that I have a fairly cheap DSLR camera, an old Rebel 2 camera by Canon, and it's not particularly good for astrophotography. It has a terrible problem with recording red light. But what I've been doing is taking fairly short exposures and then stacking them together with Photoshop, and then removing light pollution by matching the color of the sky and removing that and actually subtracting that color. And I've had a little bit of success in being able to get rid of the effects of light pollution. So, and here, this is the Hyades, the head of Taurus the Bull, with the bright orange star Aldebaran. So the Aldebaran is a foreground star. If I recall, it's like 80 light years away. But the Hyades are a star cluster that's over 200 light years away, if I remember right. Does that sound right, Chris?
I'm going to say the Hyades is out around 120 and Aldebaran's around 68, if I remember.
Okay, all right. So ballpark on my thing. But anyway, it's the face of Taurus the Bull, and but also a star cluster in the background there. And let's see. Oh, for some reason it's not advancing. There we go. All right, so another region of the moon here, and
yeah.
I'm sorry, I don't recognize the name of the craters.
Oh my gosh! Yeah, the one in the upper left is one of my absolute favorites, Tony. That's Gassendi.
Herodotus? Oh, Gassendi. Okay.
Gassendi, the diamond ring. Love
and
that.
You can see rills crossing it.
Yep.
And so this is a region that's kind of the edge of a mare on the bottom. sea, and then you see some highland material. It's heavily battered, kind of sticking up through it.
Yeah, this also is a spot where they keep thinking they see those transient lunar phenomena, like Alphonsus and all that. Descendi's another one of them.
Yeah.
So keep your eyes on it.
Yep. And then finally, Sinus Iridum, kind of a half-sunken crater, you might think of it. It's a crater that was formed and then mare material flooded over one edge of it. Just a part of Mare Imbrium is the huge mare that's down below it, although mostly in darkness. One of the interesting things you see on the mare is that it looks like it's crumpled a little bit. Those are wrinkle ridges, I guess, from the mare material actually contracting and cracking up as it shrinks. Does that sound reasonable, Chris, or would you?
It's perfect.
Would you put it a different way? I mean,
no. You're exactly right. You captured something else that I really like. Just above the Bay of Rainbows, above the semicircle in the flat spot above it, there's a little crater that's Harpalus sitting out by itself. That's the one Chesley Bonestell in the 1950s used to paint pictures of people landing on. So yeah, just a little bit above it. Oh wow.
Oh yeah.
Okay. I know what that is.
Yeah. This one actually, I just happened to be shooting the moon one morning, like at 3 a.m, and the air got extremely steady, and I noticed that the libration or tilt of the moon was just right. That Mare Oriental was visible, and that's on the top in this view. If you saw it like at midnight with the full moon, it would be on the left-hand side. That's the east side of the moon in our sky, and therefore it's called the Eastern Sea. Although, if you were an astronaut on the surface, that would be on the west side of the Earth-facing side. But anyway, it's familiar. I should have probably put in the famous lunar orbiter picture, but there's a picture from lunar orbiter which got the first really clear view looking perpendicular at this object, and it's a huge basin of rings. I mean, it looks like a bunch of bullseye with a dark spot in the middle. So it's a impact basin. It's where an asteroid landed, and then it fractured the surface in all these big circular mountain ranges that spread about 1,000 miles. Well, maybe not 1,000, but several hundred miles from edge to edge.
That's a gorgeous shot, Tony. Well, that's beautifully shown. Really is.
Thank you. And then it's the one that I'm using as my screensaver in the background. So you see the Apennine Mountains below, and what did we decide that was? Aristarchus, I guess, the big deep crater with the jagged shadow cutting through it.
Yeah, it's not Aristarchus. I'm trying to remember. It's one of the ones that sounds like that, like Aristolus or Eratosthenes is in that area. I don't.
Aristosthenes, yeah.
Yeah. Well, but it's a really beautiful view of the mountains. Look at that. That's gorgeous. And we landed there, which is cool. Right?
Yeah, we can see. This is Mount Hadley, as I recall. Oh, this thing isn't. No, it's not. I'm not able to make the pen do what I wanted to. All right. Well, we're going. Yeah, here's Clavius.
All right.
This is if you saw the movie 2001: The Space Odyssey, it's where the big city was in the movie. The one connection with Griffith Observatory is that the crater that's on the bottom rim of Clavius is Russell Porter. And Porter was, of course, the designer of Griffith Observatory.
Yeah.
He was mainly honored, well, for a couple of reasons. He did the cutaway drawings of the 200-inch Palomar telescope, which he was intimately involved with from 1928 until he died in 1948. And he did the concept, or not the concepts, but he illustrated from the blueprints cutaway drawings so people could marvel at the technology that was being designed and just even get a handle on it because it was so complex. But he also, in Scientific American, had made sketches of the moon through the 60-inch telescope. And this inspired a lot of amateurs to return to viewing the moon. People didn't seem too interested in it before, for a long time before. And so he revived interest in amateur telescope viewing of the moon. And as a result, the International Astronomical Union named the crater for him on his death in 1948.
Wow.
Yeah,
I didn't know that.
Very cool.
And then finally, here we have, let's see, Mare Nubium, I recall, right? Or is this, yeah.
Yeah, that's
I should know. I
Humorum.
mean,
It's right next door. That's Humorum with Cassandi again, right at the top.
all right. Okay, this is probably a mosaic made from that same set of pictures that I did.
Yeah.
So anyway, one thing I fear about these beautiful resolution sort of moon images is that it's going to seem very, very out of date in about like a year or two as we start to see more and more spacecraft going there. They're going to put all of the stuff to shame. So I'm glad to have learned how to do it while it was still
yeah, that's great.
This is a picture of Saturn last year, or actually in 2022, but it's the best I've done so far with it. But you can see, the Cassini division. If you look carefully, you can see the D ring, which is inside the bright, broad A ring, and you can see, so it's faintly visible around. So, but of course, Cassini did better than that. So,
wow.
Anyway, so that's some things I've been puttering around with. Besides remastering my classical CD or LP collection that I started in high school into CDs. So I'm making it from an antique thing to something that now is considered state of the art into the already passé CD form.
Although some people are now collecting CDs again, they'll be hot before you know it. Tony.
Yeah, and they're still making CDs. We gave up LPs so that nobody would ever have to deal with them again, and suddenly they're popular again. I really don't understand it, and they're way overpriced for what you get. But this isn't an audio show, so I'll shut up.
No, but I enjoy audio as well. But thank you for sharing what you've been up to, Tony. We've all been curious to find, to get back in touch with you, and thank you for sharing all the observing tips for the comet. I hope some folks send us in pictures, and those were just amazing images of the moon. Folks were just in the YouTube chat were blown away by these pictures.
Oh, thank you.
Absolutely blown away. So we'll have to check in with you again when we start doing the show in person. You'll have to come say hello to us, of course. And folks, we don't know quite when that's going to be, but let's all give Tony a round of applause here. Thank you for visiting us again, Tony.
Thank you.
Appreciated.
Good to
Very
see you.
welcome.
All right.
Now, Katie, I think you've got some pictures to share with us too, or I think you're up next, aren't you?
Yes, some more pretty pictures.
Fantastic. Take it away.
So this first one is from Uranstrom. This is a beautiful sun halo, and this was actually the astronomical picture of the day from NASA on December 21st on the solstice. I love that image. And then Maria from Denmark sent me this one. This is a geminid meteor from a beach in Denmark. So thank you so much for sending that. And this is the first sunset of winter from David Pinsky, also from December 21st. And I love this image of Jupiter. This was taken by telescope demonstrator Anthony Perkic. And on the left, you can see Io, and on the right is Ganymede. And you can actually see Ganymede's shadow on Jupiter, right on the bottom there. And then here's another one from David Pinsky, who caught this beautiful image of the setting sun on December 26th. And this is a composite of 3 images taken seconds apart. And what's so cool about this is that he caught a green flash, which is an optical phenomena that occurs when light is dispersed through the lower atmosphere during sunrise or sunset. And speaking of the sun, our sun's been very active over the last month. This was the highest monthly sunspot number in 7 years. And you can see on the graph, the predicted line is the red line and the actual is the blue. So we are having more sunspots than what was predicted so far. And then the bottom right image is from Zanol Sinal. from Turkey, who stacked 26 of these images from December 22nd to the 27th, which show more than 24 sunspot groups. And then our current sun, this is actually from yesterday, I believe, the 11th, and this shows 8 sunspots, which all pose threats for M and X class solar flares. And just today not today, but yesterday, we had the third X flare of the week. And on the left is the sun from the 9th, which shows an X class flare on the lower left edge of the sun. And then on the right is the sun from the 10th, which shows an X class flare on the top left edge. And I'll just show you. Advanced too far. There we go. Circled there. And then finally, our last pretty picture of the month is, of course, some stunning aurora. I love this image by Nicholas Hjort, and this was from Abisko, Sweden in mid-December.
Wow. Well, thank you so much for those. Those were beautiful pictures, and the sun is just going nuts. So a lot of fun to keep track of it. If you're in LA, you can always come up to Griffith Observatory when we're open to the public, of course, which is now. We are open Tuesday through Sunday. We are only closed to the public on Mondays right now. So we're back open 6 days a week. But you can check out our SALESat. We have a solar telescope, and you can see those sunspots for yourself if you happen to be in the neighborhood. Don't just look up at the sun. That'll burn your eyes, and it'll be no fun for anybody. This is a little of a not completely out of left field, but a little bit for us. We wanted to let folks know about P22, which is this mountain lion you saw here. P22 was a local favorite, lived in Griffith Park. We had a lion living in Griffith Park, and P22 recently got sick, was a very old mountain lion, so lived a long, full life for a lion, but did have to be euthanized, had to be put down because he was sick and not doing well at all, and was at the end of his life. But folks loved him, and they're going to celebrate his life in the park, in Griffith Park. So you can join on Saturday, February 4th from noon to 2 p.m. in the Greenock Theater if you wish to come celebrate P22. I was a fan of the mountain lion. It was fun hearing about making the rounds and the sightings of the mountain lion. So you can remember him, and we'll see if another one shows up sometime. They are building that wildlife bridge between the rest of the Santa Monica Mountains. So we may see more wildlife safely making its way into Griffith Park. We'll just have to see. And now it's time for our sky report, I believe. So let's see what Patrick left for us here.
Happy New Year and welcome to the January 2023 Sky Report. I'm Patrick So. Mars was in the spotlight last month. This was when the moon passed in front of Mars, creating a lunar occultation visible from parts of the Americas, Europe, and Northern Africa. This image was taken through a telescope at Griffith Observatory during our live broadcast when the moon approached Mars. This is the moment when Mars was occulted by the moon. An hour later, Mars emerged on the eastern side of the moon. On January 30th, we are in for a repeat performance. The circumstances for this month's lunar occultation of Mars is slightly different. The occultation occurs when the moon phase is waxing gibbous. The occultation is visible from southern USA, Mexico, Central America, northwestern South America, and the Caribbean. As seen from Los Angeles at 8 p.m., Mars is about 0.2 of a degree east of the moon. At 8:36 p.m., Mars touches the north limb of the moon and disappears from sight for just under an hour. 9:30 p.m., Mars emerges on the east side of the moon. By 10 p.m., Mars is about 1/10 of a degree west of the moon. Here is a close view of Mars just before it's covered by the unlit side of the moon. The occultation takes place in the northern region of the moon near the crater Plato. Mars emerges on the northeast side of the moon near the Sea of Humboldt. Weather permitting, Griffith Observatory will broadcast the Mars occultation live. Please check into our website for an announcement. And that's all for this month's Sky Report. Until next time, cheerio.
Cheerio, Patrick. Cheerio. I do want to point out to folks that wonderful seeing Patrick. There is a full version of the Sky Report with all of the highlights from the month posted on our YouTube channel. We do that on the first of every month, and be sure you check it out. You can just navigate to it, watch the whole thing, and see what's up. Also, I want to point out, folks, you do need a reservation to get to the P22 event. It was posted in the chat that there are no walk-ups allowed, so make sure you navigate to the Griffith Park website and get a reservation for that event. We don't want you showing up and turned away. And now it's time for ASC Goes to the AAS. Acronyms everywhere. On the AAS meeting, it was in Seattle, hence the little icon down below. And we managed to capture a picture of us at the AAS, as you can see here. Okay, obviously our heads aren't quite that big, although I love the expression that was caught on my face. I look like I'm thrilled about something. But actually, we attended virtually, which is why we took this virtual picture. This is the entrance to the virtual meeting. And none of us went up to Seattle this year. We all stayed here in LA. But several of us did watch a bunch of the pictures or watch a bunch of pictures, watch a bunch of the lectures and the talks, and we're going to report on them. And first, we're going to hear from some of our guide staff that are here tonight about the plenary sessions, which are the big invited lectures that everybody can attend because there's no concurrent sessions going on. And the first one we're going to hear about is about Jane Rigby, Dr. Rigby. And Bill, you managed to attend this one, and you have a report for us. Oh, I think you're muted, Bill.
Now I'm unmuted.
There you go.
I did attend this lecture. It was really terrific. Plenary, as Dr. Reitzel pointed out, means it's a topic that everybody will probably be interested in. And the topic for this one was the JWST, our great new telescope. Kavli, the Fred Kavli part means this Fred Kavli has a foundation that supports AAS quite a lot and actually provides the funds for this particular lecture. And it's quite an honor to do it, as you can see you can tell Dr. Rigby here, even with a mask on, has a big smile on her face and is very excited to be the plenary lecturer. So who is Dr. Rigby? Well, she is a PhD astrophysicist employed by Goddard Space Flight Center, and she was is the operations project scientist for JWST. I just want to point out that she had to monitor and manage a whole bunch of testing to make sure this thing worked. And then once it was up in space and in its location it was going to live in, had to make sure that the science commissioning all went well, that all the science instruments worked. Well, they all worked brilliantly. And I have to say, great kudos to her, because everybody knew at the time, we all knew that there were something like 344 components of this thing that all had to work perfectly. And they all did. And I don't know what her involvement in that is, but I think she had something to do with the fact that this telescope is an incredible success. Now, in addition to that work, she's, of course, is a working astrophysicist doing research. Oh, there it is. There's the thing that has the 344. Well, anyway, that was part of the telescope. So this is a lensed galaxy that you're looking at here. This is one of the things that she studies in her normal workaday life as an astrophysicist. This is the Hubble image of a galaxy 10 billion light years away. But it's not the stuff you see in the middle. This is gravitational lensing. You've heard us talk about it before. Just very briefly, if something that creates a whole lot of gravity, very powerful gravity, like this galaxy cluster in the middle here, if light is coming toward us from the other side of that, a great distance away, it gets bent, or appears to get bent, by the warping of space that happens when there's gravity. That's all Einstein, and he was right. So that's what those rings of light are around the edges, and those can be studied. You can get their spectra, you can understand more about them, and kind of reassemble what the object was behind. But they basically, this is a gravitational lens. It's basically nature's telescope that lets us see something that we would not see otherwise, even with our most powerful telescopes. She also worked to study the hot stellar population, which is basically very hot stars, which means very large stars. She looks at their ages and metallicities. Age, you understand. Metallicity is how much of the composition of that star is not just hydrogen and helium. Any heavier elements than that, if there's very low levels of that, then you have low metallicity. It means you were formed early in the universe, before the universe had time to create all these other heavier elements and then incorporate them into other stars. So higher metallicity means they were formed later. So galaxy evolution, she also studies. I want to point out this image here, particularly on the right. You see where it says the Sparkler Galaxy. That's something that she studied. And there are two images of that. There's one from the Webb more recently, and then the Hubble. The Hubble was a great telescope, but the Webb, you can see, just shows much more detail in that image than the Hubble did. And why is that? Well, it's partly because it's just a much bigger mirror. You can see the comparison in the size. So the much larger mirror collects much more light. It also looks at, it doesn't see optical wavelengths of light, the kind of light that we see, the red through violet spectrum that we see. It sees this stuff called infrared, which is off to the other side of red in the spectrum. And why do we study infrared? It's because infrared is longer wavelengths and they have an easier time getting through intervening dust and gas in space. So it's a good way to study really distant objects. How does all this apply to JWST? That's her previous work. Well, it's going to be her future work too. Only now she has this great, wonderful Hubble's or JWST to work with, which will get much more data than she could have gotten out of the Hubble, which was admittedly a fantastic telescope. All right. She recommended that we all go to the Flickr page for the JWST, and I did. And this is just a few little items that, a nebula there and a light curve from a transit of an exoplanet and various things. There's so much there to look at. I do recommend you also look at the Flickr pages for JWST. We're also going to be able to study the composition of atmospheres of exoplanets. So that's just amazing to me. I mean, I don't know what kind of, I don't know what we'll find. I don't even want to say anything, but it could be really, really interesting to see what kind of atmospheres some of these exoplanets orbiting other stars actually have, what their composition is. The telescope also is, I understand, easy to operate. It slews very well. Slewing, as Tony could tell you, is when you reposition the telescope from looking at one target to another. It's very, very accurate in finding those targets, and it's just a wonderful, wonderful instrument. So she was chosen to go to the White House and talk to the president and vice president about this project. And she said she really enjoyed spending this time, I'm using her language here, nerding out with the president and vice president, some other people. And as she put it, she enjoyed showing them something really wonderful and optimistic and beautiful and successful that took their mind off their normal things that they have to worry about in the world. So I really enjoyed this lecture. I'm not sure if the plenary lectures are going to be on YouTube eventually, but if they are, I would recommend finding this one and listening because there's way more than I had time to cover here. So thanks very much.
Well, thank you, Bill, for that quick update on her rundown on the JWST. It's fantastic that they were able to honor her and her hard work to make that telescope such a wonderful success. Of course, it was a huge team effort. A lot of people were involved, but Dr. Rigby was instrumental, of course. Mm-hmm. Well, next up is a report from a Dr. Stierwalt. And I believe, Daniel, you were going to tell us about this one?
I will, yes. Can you hear me all right?
You sure can. Welcome. Thank you so much.
Wonderful. Okay, so Dr. Sabrina Stierwalt right here is an assistant professor of physics at Occidental College, right over on the other side of the LA River over in Eagle Rock, California. She's an extragalactic astrophysicist studying gas dynamics, galactic formation, galactic evolution through surveys utilizing most observable wavelengths. So X-rays and infrared, anything along the spectrum she's probably seen and looked through. She's also a science communicator. So she hosts a weekly podcast called Everyday Einstein and advocates for equity for underrepresented groups in STEM fields. So it was really interesting to find out about her beforehand. But that's not what we're here for. If you go on to the next slide, we're here to talk about her plenary talk, which was all about dwarf galaxies, which she believes is an underrated topic of study in the astronomical community, and aimed to explain to the audience why they should kind of drop their current research and start observing dwarf galaxies, all in jest, of course. If you go on to the next slide, she kind of first discussed some historical context on some of our collective knowledge of dwarf galaxies. She highlighted how, although we've known about the Large Magellanic Cloud and the Small Magellanic Cloud since prehistoric times, we didn't realize what dwarf galaxies really were until Harlow Shapley discovered the sculpture dwarf galaxy in 1937. Since then, the introduction of digital surveys greatly increased the numbers, the kinds, and varying compositions of dwarf galaxies known, and we're still finding more today. If we go on to the next slide, you'll see a summary of Dr. Stilwalt's reasons of why galaxies are both hard to observe, which are highlighted in those blue boxes, or right there in the little boxes, and also important to study due to those bullet points on the image right there. If we go on to the next slide, we go ahead and talk about the first reason why we should study dwarf galaxies that she went over, was that by their very nature are very small and faint. This makes them hard to find, but it also gives them essentially they make them a treasure trove of information and structure regarding the stellar mass functions within these galaxies. Questions regarding their hypothesized numbers, locations, and their masses, and even if whether or not these dwarf galaxies can even host possible satellite dwarf galaxies, help guide modern research of dwarf galaxy formation. If we go on to the next slide, the second reason Dr. Stilwalt went over was that dwarf galaxies are much more sensitive to stellar feedback from events like supernovae. Studying the effects of the stellar feedback or events like supernovae on dwarf galaxies can tell us more about what happens during these events. They can even tell us something about dark matter, which is a hot button topic in astronomy and at the conference. Definitely. Some dwarf galaxies seem to be lacking in dark matter, and some others have a lot, apparently. So the ones that have a lot of dark matter seem to be more isolated than those that don't. And those it was really interesting hearing her talking about how mass metallicity relations can also be used to model the stellar feedback, kind of almost operating in reverse. Creating these models can actually be easier than observing the stellar feedback directly, which is something that was really cool when I heard about that. If you go on to the next slide, the third reason she discussed why we should be observing dwarf galaxies more was regarding the low metallicity environments of dwarf galaxies, and how dwarf galaxies are windows into how star formation and how their feedback occur at high redshift. We need to look into dwarf galaxies to find high redshift intermediate black mass black holes, and how metallicity can complicate things. At low metallicity, active galactic nuclei detection techniques don't necessarily work, which is it was an interesting thing to see there. If we go on to the next slide. All right. The last reason that Dr. Stilwalt went over was that dwarf galaxies are heavily influenced by their environment. As we observe further from the Milky Way galaxy, more dwarf galaxies have features like starbursts and active galactic nuclei. We can also see more mergers between dwarf galaxies. If astronomers think massive galaxies are formed from smaller galaxies merging, then we should probably learn more about these mergers between dwarf galaxies. I think it would probably be a good idea to go ahead and do that. And dwarf galaxies definitely are a great way to kind of see different types of galaxy merging. If we go on to the next slide, Dr. Stilwell then moved to talk about how upcoming surveys from the Vera Rubin Observatory and the upcoming Nancy Grace Roman telescope, as well as follow-up observations from JWST and Meerkat in South Africa, will greatly increase the number of dwarf galaxies we've discovered and what we could possibly learn from them. The last thing that she covered, how she ended her talk, of going to the next slide, was more of a focus on professional development and mentorship. Dr. Stilwalt, who is a first-generation college student, concluded her talk by thanking everyone that helped her helped her along the way, so to speak, and pointed them out individually, which I thought was a really caring touch. The final piece of advice that she gave to first generation students in the audience was to find your people, which I definitely resonated with me, especially with my experience back with the last AAS that we attended. She also recommended the book Hidden Curriculum for Mentors of First Generation Students. So that was pretty much the gist of her talk, and I thoroughly enjoyed it when I watched it.
Well, thank you for that report, Daniel. I appreciate hearing about that. It's fascinating. No, we may want to try and get her as a guest in person once we return to the Leonard Nimoy Event Horizon. It would be really great to see. Our next plenary speaker report is on Jesse Christensen. And I think, Haley, you said you were going to report on this one. What did you think of Jesse's talk? Who, of course, was a guest at All Space Considered just last year.
Yeah, exactly how I was gonna introduce her.
Yeah, sorry to steal your intro.
No, it's all good. It's worth mentioning twice. So Jesse Christensen is a project scientist for the NASA Exoplanet Archive, which is hosted through Caltech. So she is affiliated with one of the most prestigious universities in astrophysics. And so again, she's also a friend of the show's. She's a friend of many guides here at the observatory as well. So we just think she's absolutely fantastic. And she does a great job of being a pretty thorough and exciting science communicator. So if you look her up, just in general, you're going to find a bunch of different videos of talks, panels that she sat on, from very specific, like minutia of exoplanets to things like popular science. But for this plenary talk, Dr. Christensen was talking all about the study of the demographics of exoplanets, or how we image these bodies around other stars with certain characteristics of interest, how we do it, why we do it, and what we actually find, particularly looking for things that are similar to Earth. So I was able to watch her plenary talk, which was titled Towards an Exoplanet Demographics Ladder, the Emerging Picture of Planet Populations, which is a riveting title. In 2022, NASA announced that the Kepler Space Telescope had finally surpassed 5,000 confirmed exoplanet observations. And so this plot right here is actually using a variety of, or displaying a variety of methods by which exoplanets have generally been detected over the last few decades. So those are via transits, radial velocity measurements, microlensing, and direct imaging. So this plot is showing the mass of the planet relative to Earth's mass on the y-axis, and the semi-major axis orbit on the x-axis, which is basically the longest half of a planet's elliptical orbit. And so, as you can see, there starts to appear trends in the detection limits of all these different types of methodologies. And as we'll see shortly, this detection is also determined by sort of intrinsic characteristics of the planets themselves. And so the majority of the detections come from observing transits. So that's sort of the bright blue that's popping out in this particular plot. And so that's when a candidate planet passes in front of its host star, causing a dip in the luminosity of the star. And then next most frequent is radial velocity measurements. So that is essentially like the deep blue that's popping out of this plot, excuse me. And so this involves observing and measuring the host star to see if there are small perturbations essentially in the movement of it caused by the gravity of an orbiting planet. And so we can see that there are some contributions from microlensing and direct imaging shown in the peach color, a little bit harder to see because of all the transits, and then the bright green color, which is sort of to the right of the plot. And so these observations, as you can see, start to skew towards planets that are larger than Earth and orbit between 1 and 10 astronomical units from their host star. And so direct imaging planets are the smallest batch of these observations and require imaging planets with very wide orbits relative to their star. And so a plot very similar to the one that I just showed, but you might notice there are some annotations showing what the different techniques of detection are typically able to produce. So the sort of label FGKM is in reference to spectral types of stars. And just for reference, our own sun is a G-type star. So it's included in a lot of the transit and radial velocity measurements. So let's say we wanted to use this diagram as sort of a blueprint for planet hunting for Earth-like planets. And so we might be very excited to see on a plot like this that there seems to be a lot of G-type stars included, or could be included, and seem to be detected in the 2 largest data sets. And so we'll delve into this a little bit further, which was part of what Dr. Christensen was talking about. And so she's, again, interested in applying the demographic principles of exoplanet detection and occurrence. And so she talked about a term called Eta Earth. And so I've written the Greek letter and sort of the subscript E, which is basically denoting Earth. And so this is a term, a concept that is seeking to characterize the abundance of Earth-like planets in the universe. And so in this sense, Earth-like planets are defined as those between 1 to 1.5 and 2 Earth radii, and can also be described as the prevalence of rocky Earth-sized planets around a host star. So we can use the observations of the Kepler data set as well as other methods to estimate the occurrence of Earth-like planets in the universe based on our exoplanet observations. And with just the Kepler data set, Eta Earth is actually pretty hard to pinpoint. So something like an estimate of 10 to 50% of the observable planets are meeting our criteria for Eta Earth. And so in the future, with plenty of mission concepts and new instrumentation launching, it'll be quite interesting to improve upon our current understanding of the occurrence of Earth-like planets and see how sensitivity to detection improves. And so Dr. Christensen essentially ended her talk by looking at what the contribution of the Nancy Grace Roman telescope might be to a plot like this, which already shows, 5,000 confirmed exoplanets. So this plot is basically showing the anticipated detection range of the Roman telescope, which will seek to direct image exoplanets and stars around the Milky Way's galactic bulge. And so this is slated to work together with Kepler observations in order to further refine the occurrence of Eta Earth or Earth-like stars. And just to get everyone up to date on the Roman Space Telescope, it is set to launch in early 2027. So we still have some ways to go, but the patience will definitely pay off. And so this telescope is just absolutely astounding with its detection capability. Flo Spacer, Bill, and I got to visit JPL back as part of the other AAS conference that took place in Pasadena this past year in mid-2022. And we did get to talk with one of the project scientists of this telescope and learn that the Roman telescope's 300 megapixel wide field instrument, which is a mouthful but means a lot, will be capable of imaging essentially a swath of the night sky 100 times larger than Hubble, and will specifically be able to focus on the microlensing of exoplanets. So we hope, based on our current understanding of planet prevalences, that many of those rocky Earth-like planets will show up in the sort of demographics, if you will, of the Roman Space Telescope in the future. So very exciting stuff. Again, Dr. Christensen is really good about pumping up the audience, whether they are hardcore scientists or me coming from a completely different field and, working as press for her plenary talk.
Yeah, well, thank you, Haley, for that. I can't wait to have Jessie back to talk to All Space Considered. I know she'd be willing to, and she was a fabulous guest, and great report on her plenary talk. Now, on to something we call Splinter Talks, and Sarah was assigned the Splinter Talks. And what's funny about that is Splinter Talks happen, at the same time, lots of different ones, and she'll tell you kind of how that works. But we signed one person to cover the Splinter sessions where there's, 10 sessions going on at once. So good luck, Sarah. We didn't set you up for failure in any way, shape, or form. I kid, of course. So what do you want to tell us about Splinter sessions?
Well, good thing you gave me permission to select down quite a bit because, yes. And also I'm okay with failure. I do it enough. So, all right. So what these Splinter Talks are, there are two basically the similar setups, splinters and orals. And basically they are an hour-and-a-half long chunks of time that are filled with 10 to 15 minute presentations. And this is where you get the obscure stuff. These are the real niche talks. This is the juicy stuff. This is the you better know your stuff or be ready to Google it. So, for example, if we can go to the next slide, we've got this. I wanted to highlight this one because this is where the charts live. This is where the graphs live. This is the fun stuff. So this team from Caltech, their talk was called, you got a hint of it at the top. It says N8.56 keV absorption line. The full title is an 8.56 kiloelectron volt absorption line in the hyperluminous X-ray source in NGC 4045. Ultra fast outflow or cyclotron line. I love this. It's so fun. Okay. All of this is because that line in that graph, that's an absorption line. Basically, there was a chunk of light missing from this hyperluminous source. And so it tripped a bunch of alarms. We've got, Daniel talked about the sky surveys, and several other people have talked about sky surveys in various forms. Basically, we've got a bunch of telescopes that are scanning the sky all the time, and computers are scanning the light that's coming in from known sources or looking for new sources. One of these said, wait a second, we expect a full spectrum and we've got this big dropout. This needs to be further investigated. So this team from Caltech did that. And if we go to the next slide, we've got their summary. So years of work, years of modeling and in-depth research brings us to, yes, it could be a really fast outflow, but we think it's more likely a neutron star, which is super cool because we love finding neutron stars. They are a wealth of information. There just aren't enough of them. We want more. And so this team and these Splinter talks are where you get the grind of astronomy. This is where all of the PhD candidates come to give their dissertations or dissertation short versions. This is where the dial moves. This is where we get the increments, the little steps that lead to big breaks in astronomy. They're hidden gems in these Splinter talks. Okay, so we're going to go to the next slide. And my favorite of these Splinters was education and public outreach. You can tell that I'm biased. So, all right, we go to the next slide. The first section was NASA presenting on their huge success story during the 2017 solar eclipse. They had a public outreach program where they were giving away solar glasses so that people could just look up and view the total solar eclipse in 2017. They didn't stick to the center line. They went everywhere because it was partial all across the US, and they took advantage of their secret weapon, libraries. Turns out about 70% of the US population loves and trusts their local libraries and use their local libraries at least once a year. So NASA, they took advantage and they used the libraries to give out information about solar eclipses and give these glasses so that people could look. And it was such a huge success, about 1 million glasses given out. They're going to do it again and expand the program for the upcoming solar eclipse in 2024. That's right. This is a not so subtle plug for the solar eclipse that we have coming up in 2024. And we've got the next slide, which is Sci-Access. This presentation was all about how various organizations can make science more relatable, more accessible. And they called out AAS as being a good example for several reasons, one of them being quiet rooms. AAS, during this conference, they have places where people who are easily stressed out can go and just decompress, get away from the noise, get away from the people, and just reset so that they can go back out and continue absorbing science instead of having a full-blown panic attack and having to leave. Various things like this are, you can contact them and get more information on how you or your organization can make everything more accessible. And if we go to the last slide here, we've got astrophysics professor, Dr. Travis Rector of Alaska Anchorage, and he has taken a stand on disinformation. He is teaching his students step by step. Here is how you identify whether or not you are being misled, and he breaks it down into step by steps. And this, one of the steps is 3 questions: who's it by, what's the evidence, and what do the other sources say? Lateral reading. Just check everything, because if you're being lied to, it's probably going to be an outlier. If everybody else is saying, hey, global warming is happening, and this one person is saying it's not, but they're funded by the petroleum industry, maybe you've just discovered that you shouldn't trust that data. And yeah. So these are the splinters are where the gems happen, and I just wanted to share that.
Well, thank you, Sarah, for that. I appreciate your take on the splinter sessions, and indeed, that is where some of the gems happen, but it's also where some of the garbage, let's just say, I'll use a more polite term, because sometimes there, and I've been there before, students think they'll get something done, you put in your abstract months ahead of time, you work really hard, and your result just doesn't happen. You still get up there and you still explain what you've done, but there's kind of nothing behind it sometimes. So those are some of the sad cases, and but it's a learning environment. Everybody tries to be as supportive as they can, and you know, it's not easy to get up there and give those talks. So, you know, it's wonderful to see all the folks out there doing it. Well, I get the pleasure of reporting about the press releases. At each of the AAS sessions, there are press conferences where the scientists get up and they talk about their groundbreaking work. And I'm going to bring you 4 different results. Now, if you were one of the people that had a press conference, and I'm not reporting on your work, it isn't that I didn't like it, it's that there's too many of them. I can't report on all of them. And also, some of them are local, and we might invite you to come to the show. So maybe you could reach out to us first. Make it look like you want to come here. You can make us feel good, but we're going to invite some of these people to come talk. Well, the first one I want to talk about is measuring ages of stars through their angular momentum, by Marina. Anyway, I'm not even going to read the names because I'm terrible with it. My vision's too bad and the text is too small, but you can see it. Anyway, usually, and one of the best ways we could measure stellar ages was for stars in clusters. And as you can see here, this is a plot of the color of a star versus its brightness. So the color is left and right. Blue stars are on the left, red stars are on the right, and brighter stars are higher on the graph. Well, an older cluster, you'll notice, is a little tighter on the right-hand side. So you'll notice the stars on the right-hand side kind of fall down onto that main sequence. So this is an incredibly young cluster, one that's a little bit older, and now this next one's older still. Well, notice the stars in the upper left kind of peel off of that main sequence, and they continue to do so as the clusters get older and older and older. So this was a wonderful way to age date stars using the Gaia satellite, and it was able to go out there and you know, measure the brightnesses and colors of stars in clusters. We were able to get the cluster ages, and we have ages of literally billions of stars, or millions of stars at least at this point. But it's not good enough. Most stars aren't in clusters. They're all over the sky. So the Transiting Exoplanet Survey Satellite TESS was used to come up with another way. Now, what's funny is one of my professors is an undergraduate at USC, way back decades and decades ago, was working on this problem. And what you do is you use the spin state, how fast a star is spinning, to measure its age. I know, it seems kind of crazy. Well, stars slow down. Their spin rates slow down with age. And you can notice if you have a huge sample of stars, like TESS supplies, the TESS satellite supplied a huge number of stars, you're able to measure their spin speeds by looking at these star spots that are on it, basically sunspots, and you can get ages of them. So let me go forward one more here. You can see if you measure the temperature of a star, let me get my pointer here. The temperature of a star down here, and let's say we measure 5,000 degrees, and then we're able to measure the brightness of the star. We then can read off on the right-hand side that it's sort of in the greenish. Well, this is the age of the star. So a star that's you know, a little bit higher up. Anyway, I think I'm reading this the wrong way because this is kilograms, meters per second squared. Anyway, long story short, you can take a star, measure its temperature, measure how fast it's rotating, and you can get out an estimate of the age. It's not super accurate, but it can be done. It gives you an estimate. Another one I want to talk about is redshift candidate galaxies, a large number of galaxies at extremely high redshifts from JWST. So indeed, a little over a year ago, JWST was launched, and already we're getting press conferences from it, of course, wonderful releases. I just liked the title page here. It looks like a book, so beautiful work there by that. This is the first set. Now, what do we mean by galaxies at high Z? Well, we mean things way over here. See where the little arrow is pointing? So near the beginning of the universe, near the beginning of time. Here are the images they use to make these measurements. And I'm not going to explain this, but this is the method they use. They use the Lyman dropout, which I don't have time to go through it right now. But anyway, they came up with a ridiculous number of candidates. As you can see here, they have 15 total candidates that are very high redshift, and then extremely high were another, I think, 12 of them there in the red. I should make this full screen if I had half a brain. Now what's interesting about this is these exceptionally high candidates, they need to verify them. They've got to go get spectra of them. But nobody expected we would see this large of a number of galaxies with this high of redshifts. These are ridiculously early in the universe. They had to have formed very, very early on. So super interesting that we're seeing this many galaxies. They're going to have to rewrite early cosmology a little bit to be able to produce them. Another study using JWST at galaxies at fairly high redshift, 3 to 9. I never imagined I would only call that fairly high redshift. But this study is looking at the morphology or the shapes of the galaxies. Now you're all aware of this sort of Hubble tuning fork diagram with barred spirals down below and spirals up above, and then elliptical galaxies off to the side. Well, the question is, as we look back in time, how do those change? Do the ratios of the galaxies change? Do we get more ellipticals? Do we get more spirals as you go further away and back in time? And that's been measured. Well, they took these Cosmic Evolution Early Release Survey images with JWST, and they indeed found lots and lots of galaxies at very large redshifts, well, fairly large redshifts, 3 to 9. And you can compare these morphologies or shapes to the Hubble Space Telescope ones. And it turns out that, surprise, surprise, JWST is able to measure the shapes of these galaxies to much further distances. Whereas before we sort of thought the number of galaxies was declining. Well, really what was happening is the number that were unclassifiable was increasing, as you can see down below. So we just couldn't tell what they were. Well, now that we have a better telescope with better resolution, we're able to classify them. And sure enough, it turns out that nearby, the sort of turquoise or light blue color, those are spiral galaxies. There are more of those nearby, and there are fewer irregulars and ellipticals. But at a distance or a redshift of 6 to 7, they kind of even out. So equal numbers of spirals and ellipticals. And you can just see JWST is providing us with much better resolution than the Hubble images on the far left. So vast improvement there. University of Washington had an interesting survey all about measuring the Triangulum galaxy, M33. This is a survey where they want to know, well, what does this galaxy really look like? How is it put together? It's close enough that we can actually study it in detail and see what's it like. It's a smallish spiral. We have local galaxies, the Magellanic Clouds to us, but they're hard, they're irregular. Their shapes are strange. And M33 is the nearest small, really tiny spiral. Andromeda is bigger, of course, but M33 is a tiny galaxy, and it's sort of flocculent. It looks like it's kind of, I don't know, has multiple spiral arms. And like we said, visually, it's classified as flocculent in size or in shape. Well, the panchromatic Hubble Andromeda Treasury Triangulum Extended Region survey, or FATTER, and of course, that's a Julianne Delcanton creation. I love her work, and it's just, I love the acronyms that she comes up with. But she and her team took Hubble, and again, they tiled M33, and they were able to get very deep images such that you can break the field into individual stars, and you can measure the individual stars in this galaxy, and you can make color magnitude diagrams out of these. In other words, the color versus the brightness of each of those individual stars. And then you can say, well, the stars in this region are very young over in the left. The ones in the middle here are kind of young. The ones down in here are very, very old. So you can divide up the galaxy into young, middle-aged, and old, and then recreate the image of the galaxy and study its structure based upon the age of the stars. And it turns out that flocculent nature of it, sort of those multiple spiral arms, are all very young. Once you get to extremely old, you can see that it's primarily a barred two-armed spiral instead of it being multiple spiral arms. So a little bit crazy that it has two arms and a bar in the old material, but then the young, it has multiple flocculent arms. So that's our main report from the AAS meeting in Seattle. We hope you enjoyed that. We get a little science heavy this time of year, so I hope you enjoyed us diving into that. So to end tonight's show, we're going to back off the crazy science a little bit and join Chris Butler with Years Ago Today and find out what he's talking about. Chris, are you there? Are you still with us? No, he's not. We've lost him. He's muted. Very funny.
Clever boy. There we go. These January shows, they always have a looking forward, looking backward sort of thing. To look forward, we do have to remember where we've been. And I'm going to look back here a little bit farther than looking back at 2022. Actually, I'm looking back 100 years. Did anything interesting happen in astronomy 100 years ago, including locally? Actually, you know, I got a huge surprise when I looked back 100 years. There's something that happened I'd never even heard of. Which is to say, a total solar eclipse. This is the path of the moon's shadow on the Earth in September of 1923. You know, have you done trips to the other side of the world to get in the right spot where you can see a solar eclipse? I have. I've traveled a lot to do this, and I'll tell you, it was pretty frustrating for me to see 100 years ago, the moon's shadow. Look, it comes right at Southern California. Now, the reason I hadn't heard of this before, that darker purple band, that's where you had to be to see a total solar eclipse. It didn't cross over downtown Los Angeles. The city didn't get the eclipse, but the Channel Islands right offshore, right next to us, there was a total solar eclipse 30 miles away. Now, the show from downtown LA would have looked something like this, a 96% eclipse. So it still would have been spectacular. But if you wanted to see the eclipse, you wouldn't need to go the other side of the world to outer Elbonia to go see an eclipse. No, you just have to go down to San Pedro and hop on the SS Avalon to go out to Catalina. You could have sat there on the beach eating ice cream from the stands there and watch a total solar eclipse. Now, there were some land places on the mainland that got a good view, including, of all places, Lompoc. Okay, Lompoc got the shadow, and this is not a photograph, but a beautiful painting that was done of the eclipse by a space artist named Howard Russell Butler. Another space artist named Butler. Must run in the family. Here's a picture of people in Washington looking at an eclipse. 30% eclipse, but sure enough, all the politician types are looking right at the sun. It's just something that happens. On the other side of the world, here's something going on 1923 in Germany, in this case. On the roof of the Carl Zeiss company, optics makers, there's a dome that's been put up there to show their brand new device they've invented. First time the public's ever seen it. This new thing is called a planetarium, and it's going to show the stars during the daytime on the inside of a dome. I think you can catch on. Back to Southern California here. Hubble news, not the telescope we know, but the man, Edwin Hubble, alive at this time and a busy researcher up at Mount Wilson Observatory, just north of Pasadena. This is the year we've talked about the famous M31 there, the Andromeda Galaxy. Well, at this time, it was called the Andromeda Nebula. They weren't entirely sure what it was, and they thought it was lying somewhere in the outskirts of our galaxy, the Milky Way galaxy, the only galaxy at the time we thought. But at the end of this year, in 1923, Hubble makes an observation and proves by detecting a variable star that he proves that the Andromeda Galaxy, they can measure, they can calculate its distance. It lies at a tremendous distance. The universe is much bigger than we thought it was, and Andromeda is another galaxy. It opened up that whole area of research we were just talking about. That started in 1923, 100 years ago. It started right here in Southern California when he wrote VAR on that plate. It wasn't talked with like a pirate day, but VAR, that's what it means, variable star. Books, if you're looking to read in 1923, may I suggest Hermann Oberth's brand new book, The Rocket into Interplanetary Space. Now, a lot of people had daydreams about sending rockets into space, but what Hermann Oberth has done is he's connected that with solid mathematics and even engineering proposals, proving that rockets really could navigate the solar system. This is a very exciting new book, and the math is there. It's solid. Even young high school students like Werner von Braun are picking up this book and starting to get ideas. Will something come of it? I think in the future, yes, it might. Speaking of the future, the children are our future. Here's some 1923 babies for you. We have got the legendary UK science popularizer, Sir Patrick Moore there. He's a 1923 baby. I'm betting he was born with a monocle in his eye. And talking about rockets, well, Alan Bartlett Shepard is born in the United States, and he'll take one of those rocket rides to become America's first man in space. And then we also have Dr. Freeman Dyson is a 1923 baby, and he's going to come up with wild ideas that would have terrified people in 1923, like alien civilizations building shells around their star to harvest all the energy of a sun. So some forward-thinking people paving the way towards the future that you and I live in now, 100 years in the future. So there's a little look back as we take our eyes and look ahead towards 2023.
Well, thanks for that, Chris. That was interesting. And indeed, Freeman Dyson, one of the most forward thinkers out there. Just yes. Amazing. Some of the concept he came up with, the Dyson sphere, indeed is a fabulous one. Well, folks, we're at the end of All Space Considered. I want to thank everybody that joined us tonight. All of our panelists, Anthony Cook, Tony Cook, thank you for coming back and joining us this month. Great fun to see you come back in person. Once again, Griffith Observatory is owned and operated by the City of Los Angeles, operated by the Department of Recreation and Parks. And we always like to thank Griffith Observatory Foundation, who's our nonprofit partner. And if you like this sort of stuff, we recommend you join Griffith Observatory Foundation. You get more opportunities to engage with space and science and Griffith Observatory and people like you. And we thank all the members and everybody that's donated again. So thank you for joining us tonight. We'll be back next month with an all-new show, and we'll let you know which day we're going to be on. I kind of like these Thursdays, but then again, that means I have to work tomorrow. Normally I'd be off tomorrow. So we'll see what we decide to stick with. If you have an opinion on it, let us know. Tweet at us or send us an email or whatever you want to do. Send us an Instagram DM and tell us, no, I didn't like the Thursdays, or Thursdays were great. We'd love to hear from you. So thanks everybody for making this show so special. Thanks correspondents, wonderful job tonight. And thanks tech crew that are up there at Griffith Observatory in the booth. Brendan and Michael, we appreciate you guys being up there for us. So have a great night, everybody. We'll see you next month.
Good night.